Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on nonlinear control systems theory. Today we are going to continue our discussion on sliding mode control, and this will be our second and last discussion on this topic. So far we have discussed about sliding mode control, that the sliding surface has two selection criteria. First is that the sliding surface should be chosen such that S is equal to 0 should help in achieving the control objective. And the second condition for selection of sliding surface is that you have to make sure that the relative degree of the sliding surface is 1. That means that u should appear in control input should appear in the first derivative of the sliding surface. Then we also looked at the controller design part, that first you choose the partial expression for u to cancel out some known terms, and then you calculate the remaining part of u to ensure the sliding condition. Alright, so today we are going to look at a couple of more examples to get more insights into the sliding mode control. So first of all, we are going to look at a third order example, which is a triple integrator system. And the triple integrator system is such that the derivative of the first state is the second state, and the derivative of the second state is the third state, and the third state has a control input in its derivative. So this system is known as triple integrator system. And let us assume that the output of the system is x1, and we want to drive the output to 0. So our control input is to drive the output of the system to 0. Since u appears in the derivative of x3, and we know that we have to have u in the derivative of the sliding surface, so whatever sliding surface we choose, we must have x3 in the sliding surface. So consider this sliding surface, S is equal to x3 plus x2 plus x1. So here choosing the sliding surface like this will ensure that u will appear in the derivative of the sliding surface. But the problem is that we have also another guideline, that putting S is equal to 0 should achieve our control objective. So how does this sliding surface, when we replace S with 0 here, so how does x1 plus x2 plus x3 equal 0 achieves x1 equal 0? So answer to that lies in the structure of the problem. If you look into the structure of the problem, you can see that if S is equal to 0, then this implies that x1 plus x1 dot, which is x2, plus x1 double derivative, which is x3. So all the derivatives of x1 and the x1 itself, so sum of all the derivatives of x1 and x1 itself is 0. And if you think about it, since our desired value of x1 is 0, so this means that this is the error term, this is the derivative of the error, and this is the second derivative of the error term. So in this way you can say that if all the only way S is equal to 0 is sustainable is to have all of these three simultaneously 0, because assume that S is equal to 0 but S is equal to 0 is achieved with some non-zero value of any one of these three. So if x1 is non-zero, then that will mean that these derivatives will also have to be non-zero in order to cancel out x1 and make the whole sum equal to 0. And if any of these is non-zero, that means that x1 will change. So these are rates of change of x1. This is rate of change of x1. If this is not 0, then it means that x1 will keep on changing, and that will refrain the S from being 0 sustainably. And then if this is non-zero, then it means that the rate of change of x1 is changing itself. So that in turn will change the x1. So the only way to render s is equal to 0 is to have x1 is equal to 0 and the derivatives of x1 to be 0 as well. Alright, so we will look so this is the system, this is our sliding surface. I've had some discussion about why this sliding surface makes sense, and we will see later on by the end of this example that in fact this sliding surface is okay to define the sliding surface like this. So in this case S dot will be x3 derivative of x3, which is u, plus derivative of x2, which is x3, plus derivative of x1, which is x2. And since all of these two are known to us, we can define and also u appears in the S dot, so this condition is satisfied as we already could predict. So next we either use the Lyapunov approach to find u, that renders s equals 0 as t as s approaches 0 as t approaches infinity, or we can just simply try to achieve the sliding condition with the help of u. So both are equivalent. So this is our sliding surface, x1 plus x2 plus x3. This is the derivative of the sliding surface, and what we do is we try to satisfy the sliding condition by selection of u. So we write s into s dot equal s times, we put in the expression for s dot, and then if we pick u to be minus eta sine of s minus x3 minus x2, then x2 and x3 will be cancelled out, and what we will have inside the bracket will be minus eta sine of s, and when this is multiplied by s, then the sliding condition is satisfied. So this, remember that the sliding condition has an inequality which is like less than or equal to, so equality basically does result in the satisfaction of sliding condition. So this is the final control law that basically renders the system asymptotically stable using the sliding mode control. Okay, so we look at the results. When you simulate the trajectories of this system, so when you simulate this whole system with u as we developed with the help of sliding mode, then the trajectories are something like this. So we start with the initial condition of x3 initially is 3, x2 is initially minus 2, and x1 is initially 1. So when we apply the sliding mode control, so within let's say 10 or 12 seconds the system is stabilized. Control objective, remember the control objective is to have x1 going to 0, but in this case not only we achieve the control objective, but the only way to achieve the control objective sustainably is to have both all x1 x2 x3 equal 0, because the system is in integration form, or it is also called controllable canonical form. So this looks so far so good, but I just want to point out something here, that if you zoom in this part, so this part looks very nice here in this graph, but if you really zoom this in, you will find that there is 10 to the power minus 3, very small, but there are errors. So, and not only that there are errors, but you can see that the lines are still not steady, so they are still moving. So this is x2, it's going up, and maybe it will settle and come down again. This is x1, it's going down and trying to go up again, and this is x3. So notice that this line of x3 is thicker than the lines of x1 and x2. This is not because I plotted it like this. This line is thick because there is some chattering going on. So in the state x3 there is some chattering problem, so this is switching, like this is wiggling at a very high frequency. That is why this thickness is more than the other two lines. And also the chattering begins when you achieve this kind of steady state. In the beginning, like in this zone, when you are still in the transient phase, the thickness of this red line is equal to the thickness of green and blue line. So there is no chattering until you reach sort of there is a reaching phase when you're trying to reach the sliding surface, and then there is the sliding phase. So when you're in the sliding phase or trying to maintain the sliding phase, trying to keep within the sliding surface, then there is a lot of chattering. This sign of S is changing at a very high frequency. So this chattering problem is well studied in the literature. Unfortunately, we do not have enough time to discuss chattering or the solutions of chattering in this course, but I strongly encourage you to look at it on your own. Alright, so another example. So in the previous example, you might have noticed that we did not incorporate any uncertainties, while the major advantage of sliding mode control is that it deals with the uncertainties. So we must have another example, and this is another example of a second order system where we have x1 dot equals x2 and x2 dot equals theta 1 times x2 square plus theta 2 times x1 plus u, and here theta 1 and theta 2 are unknown uncertainties in the model. So this uncertainty is proportional to the square of the value of x2, and this uncertainty is proportional to the value of x1. So here you also know from the previous lecture that in order to cater for the uncertainties using sliding mode control, we need to at least have upper bound on the uncertainties. Here I assume that theta 1 and theta 2 are both positive uncertainties and they have some upper bound. So theta 1 is bounded by A and theta 2 is bounded by B. So so A and B are some positive numbers. So our control objective in this case is to drive x1 and x2 to 0. So here you can also notice that this is also a double integrator type system. x1 dot is equal to x2 and x2 dot is equal to u, except that in this double integrator we have some uncertainties involved. Alright, so here is the system again, and now we will discuss the solution of this control problem related to this system. So we let the sliding surface to be x1 plus x2, very similar to how we let the sliding surface in the previous example as x1 plus x2 plus x3, because that was triple integrator and this one is a double integrator. So we have the sliding surface to be x1 plus x2, the sum of all states. So this is something that you can do for controllable canonical type systems, and for linear systems using the state space transformation you can always convert a system into controllable canonical form. So you defining the sliding surface like this will result in the derivative of sliding surface to be x2 plus theta 2 times x1 plus theta 1 times x2 square plus u, and you can see that u appears in the derivative of the sliding surface. And now we cancel the known terms using, there is only one known term x2 here, so we make minus x2 appear in the expression of u to cancel this out, and then we have other part of u still to be decided. And then we update the expression for the derivative of sliding surface, and then we remember that theta 1 is less than A and theta 2 is less than B. So we can say that S into S dot is less than or equal to S times the expression for S dot, which is V minus. So we replace theta 2 with B and we replace theta 1 with A. And then alright, so you can also have you can also select V is equal to minus negative of minus bx1 plus ax2 square plus sine of s. Alright, so actually the sine of s will be multiplied with this and this term as well. So there is a slight typo here, because this will be multiplied by sine of s, this will be multiplied with sine of s, and the expression for v will be minus bx1 plus ax square plus 1 whole multiplied by sine of s. So this, I think this is a mistake here, and I apologize about this mistake. So this is s into s dot. We can have s into s dot less than equal to minus sine of s with this type of controller, except as I mentioned, v would be sine. The sine of s will be multiplied with this whole term, and here there will be sine of s with these two terms, because we are assuming this theta to be positive, and there is a negative sign here, so we have to cater for that. And so then u will be minus x2 minus bx1 minus ax2 square plus 1, and this whole three terms will be multiplied with the sine of s. Okay, so the above controller stabilizes the given system, and when you look at the trajectories, these are the trajectories, and you can see that the systems are both of the states converge to 0. We start with the initial condition x1 equal 1 and x2 equal minus 2, but if we zoom, you can see that there's 10 raised to the power minus 3. This is a very small error, but there is still some error after 7 seconds, which looks like that it will go away, but if we further zoom in this part, then as I said earlier, there is some chattering in the x2 states. Sorry about that. So you can see that there is some chattering here, which is basically telling us that chattering is a real problem in sliding mode control, which encourages you to look at the solutions of the chattering in the literature. So in order to conclude, we see that selection of the sliding surface may involve higher derivatives of the error and terms other than the error, as long as, well, so far we have not included any term other than the error. We have just included first and second derivative of the error, as long as the only sustainable way to keep s equal to 0 is to have error approaching to 0. So you have to be very careful that however you define your sliding surface s, the only sustainable way to keep s equal 0 should be by making the error approach 0. Or as long as the system is in controllable canonical form, every next state is the derivative of the next state is the derivative of the previous state, then it is easy to define the sliding surface as sum of all state variables. And then we have also seen that chattering is the real problem. So that is all I want to discuss in this part of the discussion on sliding mode control. So in the end, I recap all that we have discussed in a couple of minutes. Okay, so we are ready for the recap of the lecture, and we look at what we did today. So far we reviewed the conditions for selection of the sliding surface. So first of all, the sliding surface should be selected such that s is equal to 0 should help us in achieving the control objective, and then we should make sure that u appears in the derivative of the sliding surface. Then we first select u partially to cancel out the known terms, and then we select the remaining part of the u to ensure the sliding condition. We looked at two examples today. First example was the triple integrator system. We selected the sliding surface, and then we discussed how s is equal to 0 in this case achieves x, or should achieve x1 equal to 0, and then u also appears in the S dot, and next we selected u to cancel out the known terms and to achieve the sliding condition, which was straightforward. And then we looked at the simulations of the corresponding system with the designed control law, and we looked at the chattering problem here, that one of the states is it's showing high frequency vibrations. And then we looked at another example. So double integrator system, but with some uncertainties involved, bounded uncertainties with known bounds. And then we looked at the solution of this system. We selected the sliding surface as sum of all state variables, as with we did for the previous example. S dot in this case does have the uncertain terms involved, so we can select u to cancel out the known terms, but we will cancel out the unknown terms. So we know that. So here when I went through the lecture first time, there was an error here, which I have now removed, and this is the correct way to write these things, because in order for this to be less than equal to 0, there should be sine of s multiplied by these two numbers. And then we have v is equal to, this is the correct expression for v. When I went through the lecture for the first time, it was incorrect, and now I have corrected it, and this is the final correct expression for u. And I've also updated the figures, which did not well, in this case the error did not result in any substantial change in the trajectories. But these are the correct trajectories, which are very similar to what we saw when we went through the lecture first time. And when we zoom this in, we see that after these states are still converging towards 0, but one of the state is indicating the chattering. And we further zoom this in, and we can see clearly that this state is not doing the chattering, but this state is doing the chattering. This is the state x2, and the u control input appears in the derivative of x2. So this state is affected by the switching of the control law more than the x1 state. So we have conclusions that we can have s as anything as long as the only sustainable way to make s equal to 0, or to keep s equal to 0, is by having error approaching 0. And chattering, we also looked at the chattering problem. So that is all about sliding mode control, and I hope you were able to understand the lecture. And if not, you can ask me questions